Hello, grade 11s. This class is taking place Tuesday, May 19th, Coronachem day 31, period 1. And this is the answer to your homework question. The homework question was based on a hypothetical concentration of gold in the ocean. I asked if the ocean contained 1 microgram per liter of gold, how much would be found in a kilometer cubed of ocean water. And this is a thought experiment that you could conduct before you would embark upon say a commercial venture to find out whether it's even feasible to undertake such a labor. And we'll see in a moment that it would not be, but not based on what I said necessarily. There are other indications. Anyway, to answer the question, you start off by finding out how many liters there are in 1 kilometer cubed of water. So in a 1 kilometer cubed, remember, you would have a cube that was a kilometer high, a kilometer wide, and a kilometer long, completely filled with water. So that would mean 1,000 liters in all 3 directions, and that's what this is all about. I'm converting a kilometer into meters, but I'm raising it to the power of 3 because it's a 3-dimensional thing. And then I'm also going to multiply it by 1,000 because there's 1,000 liters for every meter cubed. To avoid using a calculator, I just converted everything to powers of 10. So if you raise 1,000 to the power of 3, you'll get, it's the same as saying 10 to the power of 3 to the power of 3, because 1,000 is 10 to the power of 3. So 10 to the 3 raised it to the 3 becomes 10 to the 9. And then also remember that the cubed, the power of 3 is also distributed to all the other things inside the bracket, to the meters, to the 1, and to the kilometers. If you raise 1 to the power of 3, you still get 1. And I wrote that here. So once everything is raised to the correct power, you can eliminate a lot of things. You can eliminate kilometers cubed, eliminate meters cubed. You're left with an answer in liters. So a kilometer cubed of water is 1 trillion liters of water, 10 to the power of 12. If you take 1 trillion liters of water and their content of gold is 1 microgram per liter, you'll have 1 trillion micrograms of gold. Trillion micrograms, so there's a million micrograms per gram, so 10 to the 6. That means you have 1 million grams of gold. And then the million grams we know is there's 1,000 grams, 10 to the 3 grams per kilogram, so that would equal 1,000 kilograms, and 1,000 kilograms divided by 1,000 gives you a ton. So if ocean water were to contain 1 microgram per liter of gold as a concentration, you would be able to extract a ton of gold from a kilometer cubed of water. As it turns out, the concentration is actually 5.0 times 10 to the minus 9% by mass. So if it's a percent by mass, it would turn into 5.0 times 10 to the minus 11. So 5.0 times 10 to the minus 11 parts. Put it another way, it would be like saying if you had 1 kilogram of seawater, if you had 5.0 times 10 to the power of 11 liters of seawater, you would have, or 1 kilograms of seawater, you would have 1 kilogram of gold. And I redid the calculation for 1 kilometer cubed, you would get 2 kilograms of gold. So the actual content is 500 times less than I said. It's 1/500th of a microgram, or half a nanogram. Oh wait, it's 5 nanograms per liter. Yeah, that's the seawater content of gold is 5 nanograms per liter. So in 1 kilometer cubed of seawater, you would get 2 kilograms of gold. That's a lot of gold, but the amount of work that would go into extracting it would not make it very profitable. However, if you were to embark upon such commercial venture. There are other minerals in the water that would be of commercial significance. There's lithium, you might have chromium, you'd have platinum, and other precious metals would also be found in seawater, because remember, seawater comes from rivers and lakes that have drained into the ocean, and all the water that collects in the oceans has first run over the land for the most part, well, unless it falls directly in the ocean, but if it runs over the land, it leaches minerals from the rocks at very low concentrations. But imagine this happening over the course of billions of years. Over time, the concentration would build up to noticeable amounts, and that's exactly what has happened. And the oceans are a rich repository of many useful minerals, and I think in the centuries to come, the oceans will actually be where we get most of our resources from, as far as minerals are concerned. That and a lot of recycling, because in a technological society, there's already a lot of metal floating around. You know, cars get recycled, everything. If you recycle a lot, then there's a treasure trove of things in technology. The next thing I wanted to mention was green chemistry. It's the last thing we're going to do in this chapter, and then we're going to do the answers from the last test I gave you, and then we'll start our review. And that'll get you ready for university to the best of my abilities, even though I've been doing the equivalent of teaching through a drinking straw, because that's what this feels like. But hopefully you got something out of it. So let's look at green chemistry. I'm disappointed to see that there are still a few students who basically have decided they're going to check out. And it's to your detriment. You probably don't need this course, but if you do need the course, you're going to end up taking it over, basically. This is not a bird course. You cannot fake chemistry. And if you go to a university program, you'll find out very quickly. So green chemistry. This is not to say that you can fake any other subject matter. If you take anything seriously, you'll do it well. And I have no respect for people who don't take the trouble to do things well or take advantage of the situation. I was reading an article today about how simply returning a shopping cart can say a lot about a person. You know, there's no pressure, there's no laws being broken if you don't return a shopping cart. And because of that, many people have I've done it myself. People just leave the shopping cart in the middle of the lot. But think about that for a moment. Somebody has to go and gather them around and bring them back. But the store just asks us, please put them in the bay. Or you put them in that little area where they collect them. The kid who has to go running around the parking lot collecting the shopping carts will have a much easier time of it. So it's little things like that make for a better society, when people actually care about what their actions will do to others. Green chemistry is designed to prevent waste, avoid using toxic substances, use energy efficient syntheses. I guess that's plural for synthesis, because you wouldn't say synthesises. Use catalysts to boost efficiency. And reduce the use of solvents. Well, here's an example of a not green synthesis. Phosgene is a carbonyl compound with two chlorine atoms. It's a great cross-linking agent. It's actually pretty dangerous though. It's toxic. I tried ordering some once when I was the chemistry teacher at another school, and they wouldn't let me buy it. Not the school, but the whatever regulatory body controls chemicals. They wouldn't let me buy it because apparently it's one of the building blocks for making nerve gas. I had no intention of making nerve gas. It was just, I guess they were controlling that. I guess it's justifiable. But they're always watching. They're watching chemicals. You know, if you go and buy things like the precursors for making methamphetamine, you can bet your bottom dollar somebody's going to be watching, and they should, because methamphetamine destroys many lives. And Phosgene, if it was allowed to fall into the wrong hands, could be used to make all sorts of horrible things. So I guess I don't oppose that idea, but you know, there are moments when the government oversteps the bounds of what would be privacy. Well, that's a thorny subject. At what point is privacy so sacred that we are willing to die for it? That's the question. All right, so you start off with bisphenol A and phosgene. And this is what you get. You get this cross-linked plastic known as lexan polycarbonate. Made of these repeating units of the bisphenol and the phosgene, which has now lost its chlorine atoms because it is connected to the bisphenol. And that repeating unit is what we call a polymer, and it makes a useful plastic. There's the repeating unit. And then you also get two hydrochloric acids, two equivalents of hydrochloric acid from that. So this is called lexan polycarbonate. Now, you could make the same chemical if you replace this molecule with something called dimethyl carbonate. And dimethyl carbonate, the green version of that. Now, you know, it's not always as ideal as you might think, because replacing phosgene with dimethyl carbonate won't necessarily give you the same amount of I don't know what the actual percentage of yield is. I don't know if it has the same efficiency, but you could replace this molecule with this, and you probably would still get, you know, reasonable synthetic results. This is called dimethyl carbonate, and it's not toxic. At least it's not as toxic as phosgene. So that's a suitable replacement. A suitable substitute for phosgene, which is environmentally more friendly and less toxic to whoever's using it. If you accidentally breathe in phosgene, I'm pretty sure it's not good for your lungs. Not that I would advocate breathing in dimethyl carbonate either, but it probably would be okay. And then you're talking to someone who has pretty sensitive lungs. Yesterday I stepped into a place where there were a lot of wood chips, and I was clearing some blockages out, and a lot of dust was floating in the air. That's why I'm coughing today, because I breathed in a lot of that dust. And it irritated my lungs. I was coughing up phlegm last night. I'm still coughing a little bit today. The next thing I want to look at is the chlorination of water. Of course, water has to be purified before you drink it, so you get it from a river. There are multiple steps they go through to get rid of the sediments that are floating in the water. They sometimes add substances called flocculation. I forget what the rest of the name is. They're flocculants. They're substances that cause the formation of little flakes, like snowflakes, and then all the stuff that sticks together goes to the bottom, and it clarifies the water. That's the first step the first step of purification. And then they have other steps where they filter it through sand or other substances. And then finally, when the water is reasonably pure, they filter it through a more high-grade filter, or they make it undergo reverse osmosis to extract pure water out of salty water. And as a last step, they add something to kill germs, usually chlorine. Chlorination of water, though, is known to produce halogenated methanes, because when you add chlorine, if there's any organic substances in the water, the chlorine can react with the organic substances and then chlorinate them, and it doesn't remove them from the water. They just sit there in the water. And chlorinated substances can be toxic. They tend to be usually quite fat soluble. So the less you ingest them, the better. On the other hand, if you don't put chlorine in the water, then you're taking the risk of ingesting some bacteria or virus that could be harmful to your health. So there has to be a compromise between affecting your health with the things that you're using to disinfect the water and affecting your health with things that would be lurking in the water if you didn't disinfect it properly. There are multiple ways you can purify water. It doesn't only have to be through chlorination as the last step. And they say in the notes that I took that the World Health Organization, which just lost its funding in the US because Trump caught them lying. And isn't it wonderful that our own Prime Minister quickly jumped in and replaced the funding with our money that Trump had taken away. Not batting an eyelash, not questioning why would he do that. No, that's okay. We have lots of money here. We can just give it away. I do not approve. It's my money also. Anyway, the World Health Organization did once say that trihalomethanes, basically methanes with 3 chlorine atoms on them, should not exceed 80 micrograms per liter concentration. So obviously they're recognized as toxic. An alternative to using chlorination to make water safe is to use ozone. But even ozone, when it's bubbled through the water, it oxidizes things quite aggressively. Even ozone, when it oxidizes certain substances, it can activate them and make them more toxic. So it can still leave toxic byproducts. Yet another way of preventing water from having live organisms that could cause disease is to irradiate it with UV. So there's more than one way of purifying water. And I'm sure research is being done or has been done in the past to find the best, most cost-effective and safest way of producing clean water that is drinkable. The other thing they do, which I find controversial and which should have been stopped a long time ago, is the addition of fluoride to water. There should be no fluoride in the water. And they're always trotting out this this idea that it's good for your teeth. Yes, big deal. It's good for your teeth. It damages intelligence. And I'm convinced it causes thyroid disorders because it's a halogen. Fluoride is a halogen. The only halogens you need in your body are chloride and iodide. The other ones are not needed. And let me show you. On the periodic table. And I feel pretty strongly about this because there are studies published where they have shown that fluoride reduces intelligence. I don't know if they've proven that it destroys thyroid function, but let's just analyze it for a moment. In the periodic table, you have fluorine, chlorine, bromine, iodine, and astatine. Astatine is AT, sorry. Okay? You need chloride and you need iodide, tiny amounts of iodide. If you don't have iodide in your diet, especially as a child, you suffer from something called cretinism. Your brain fails to develop and you damage the intelligence of the child. So you absolutely need iodine to make thyroid hormones and to have normal development. You also need chloride to maintain osmotic balance in your cells and in your circulatory system. But they do add fluoride. And astatine, of course, is not available on the surface of the earth because it's radioactive and it turns into something else. So fluoride and bromide are two halogens you do not need in your body. Bromide is maybe not as toxic, although don't quote me on that either, because they don't know all the pathways that bromide can go into. Suffice it to say, they used to make a substance called bromoseltzer several years ago, and it was a neurotropic. It was not a neurotropic, an anxiolytic. It was something you would take to calm your nerves. If you wanted to fall asleep at night, you'd have a little bag, you'd rip it open, put it in, the thing would fizz, and you'd make it was called bromoseltzer. But they discovered that having high levels of bromide in your body was correlated with nervous disorders, and a significant number of people who had very serious psychiatric problems also had high levels of bromide in their system, probably because they were self-medicating, but it tended to make them worse over time. So they quietly discontinued using bromides. They actually put a word in the lexicon. A bromide is an ineffective solution to a problem. Problem is referred to as a bromide, and that's where that comes from. We still find bromine in foods, though. It hasn't been outlawed completely. You still find bromine in food. If you look at hydrogenated vegetable oil, they sometimes add bromine to increase the density of the oil so that it stays mixed into water. Because if you add oil to water, the two separate. You can't get them to stay together. So one of the things they do in the food industry is they'll use brominated vegetable oil, and by adding bromine, they increase the density just enough so that it matches the density of water, and it stays in suspension because it has neutral buoyancy within the water. So there are drinks that have bromine in them. There are foods that have bromine in them. I never put that in my body because you don't know where the bromine ends up. Your body metabolizes the fatty acids, but you don't know what happens to the bromine atoms after your body breaks down those molecules. My guess is they probably interfere with the metabolism of fatty acids. So I would not recommend eating or drinking anything with bromides in it or bromines in it. Lastly, fluoride. They still put it in the water because they say it makes your teeth stronger. You know, it mixes with the hydroxyapatite mineral that is in the enamel of your teeth, which is the hardest substance in your body. It's about as hard as steel, which is why a dentist can scratch your tooth without scoring your enamel, because the hardness of the enamel is about the same hardness as steel. It's a very hard mineral. And adding fluoride makes it even tougher to acid attack. But I would say instead of fluoridating human beings, just get them to brush their teeth, because the enamel is quite strong on its own accord. And instead of throwing toxic waste into the water, because that's what fluorides are. Fluoride is toxic waste. If you buy any fluoride, you'll see, skull and crossbones will be on the container. Don't get it on your hands. Don't ingest it. Wear gloves when using it. So why are we putting it in the water? Yes, I know the concentration is low. I think it's a bad idea, and it should have been discontinued years ago, and yet it persists. So your chemistry teacher disagrees with the use of fluoride in water. So that should be removed. Okay, so the only two halogens you really need are these two. Okay, that concludes this chapter as far as I'm concerned. I'm going to give you one last little bit of homework, and that is number 1827 in the textbook. Let's see if you can do it. I'll give you some hints because you won't get it without the hints. Here it is. So before I show you the problem, I'll show you the hints you need to get it. First of all, you'll need the formula lambda mu equals c. Lambda equals the wavelength of light in meters. Nu is the frequency of light in hertz, which has units of seconds to the -1, and c is the speed of light, which is 3.0 times 10 to the 8 meters per second. Okay, you'll need that formula, And you're also going to need Planck's formula. The energy of a photon of light, of a single photon, E is equal to h nu, where h is Planck's constant, which is 6.626 times 10 to the negative 34 joule times second. Nu again is the frequency that I mentioned here, and E is the energy of one photon. Okay? So that should be everything you need to solve the problem number 1827 on the text, which is your homework. And then tomorrow I will give you the answers. Also tomorrow I'm planning to give you the answers to the last test we did. Now let me show you the question itself. First I'll read it for you, and then I'll show you the question. It's chapter 18, number 27, I said. Yeah. Okay, the question is this. Alcohol-based fuels for automobiles lead to the production of a formaldehyde, CH2O, in exhaust gases. Formaldehyde undergoes photodissociation, which contributes to photochemical smog. So they show CH2O, which is the formula for formaldehyde, plus Hv, which symbolizes light energy, turning into CHO plus H. So it dissociates the formaldehyde into a radical molecule. The maximum wavelength of light that can cause this reaction is 335 nanometers. A. In what part of the electromagnetic spectrum is light with this wavelength found? And B, what is the maximum strength of a bond in kilojoules per mole that can be broken by absorption of a photon of 335 nanometers of light? C, compare your answer from part B to the appropriate value from table 8.4. What do you conclude about the CH bond energy in formaldehyde? Write out, and D, write out the formaldehyde photodissociation reaction showing Lewis dot structures. And I did all of that, and I'll show you tomorrow what I did if you get stuck, so don't worry. But here is 1827. That's the first part, and the second part is, where did I put it? It's up here. And you need also one other thing, table 8.4, which I'll let you have a look at. 18.4, sorry. Table 18.2, already passed it. 18.4, there it is. No, that's not it. Was it the table they were pointing out? No, 8.4. Okay. Table 8.4. Okay, there's the average bond energies. And I'll explain it tomorrow when we go over it. Okay, so we'll see you tomorrow.